Hello everyone. So this is, in this section, we're going to talk about the unit tangent vector and the unit normal vector. So this might be a slightly longer video than the others and a little bit more technical because I want to go through it somewhat more slowly than usual. So let's start with the unit tangent vector. Right, so imagine you have a curve, this green curve over here, which we call C, and it's given by some parameterization, R of t, right? So this could be a curve in space. I drew it as a curve in space, so it's not really intersecting. If you like, think of this in space, and then this is the plane below it. Then the shadow of the curve might just look like this. Right, so there's no real intersection here. It's just curving on itself, right? Okay, so you have your position vector r, right? And you have r, the derivative of r, which is this red vector here, right? And we can think of this also as the velocity vector, as we did in the previous section, right? So if we only want to consider, right, the curve itself, right, the geometry of the curve, right, we don't care that there's a particle moving along the curve, right? We just want to consider the curve by itself, right? So that's one reason why we don't care how fast this object is moving. We just want to know what direction it's moving in. And so we would like to make a vector that doesn't change its magnitude. It doesn't change its length, right? So we want to make it a standard length. How about 1, right? So we can always make this vector, this red vector here, we can normalize it, right? That means we can make it a unit vector, right? So in that case, right, however fast it's going, the unit tangent vector will point in the same direction, but it's going to maintain the same magnitude, right? So at each point, right, you might have the unit tangent vector is not changing its length. It's just pointing, oops, I made it at a little longer, I think, right? All it's doing at each point is pointing in the direction of the curve. There's no right, essentially the speed is 1 at each point, right? So the vector is changing. It is a function of little t. Little t you can think of as time, right? But it's just our parameter, right? And so, yeah, all these different vectors will change through time, but the length will not change. The length will be 1. As opposed to the velocity, right? The velocity could change its length. It could be shorter in some cases, slower, right? And then in other cases, it could be moving very quickly, right? But yes, we don't care about how fast it's moving, right? The unit tangent vector will have the same magnitude, the same norm. It will always be 1. So let's make that clear, right? If I take the magnitude of t, capital T, right, as a function of little t, regardless of what little t is, this will always just be 1. It's a constant, right? Okay, so that's the idea of the unit tangent vector. You take the derivative of r, and when you divide by its magnitude, you divide by its norm, you get a unit vector, right? You normalize the vector. Right? So we're going to do 2 examples of this. I'll start with the first one. The first one will be kind of an easy one, right? So suppose r is just the vector with components, and we'll make it a plane curve, right? So the components will just be, let's say, t cubed and t to the 4th. Okay. So, and this is for all t, let's say. So here, my open interval, could just be all real numbers, right? Right, and that may or may not mean that it's an infinite curve, that the curve goes on forever. I think in this case it does, pretty much, but in other cases, you know, it could be a finite interval and go on forever. It could be an infinite interval and, you know, not go on forever, but here I think it does. Right, so the question is just to find the unit tangent vector t as a function of time. Right? So just apply the definition, right? First we need the derivative of r, right? And then I'll keep writing it this way, right? So this will be 3t squared for the first component and 4t cubed for the second component, right? And now we need to divide by its norm. So let's take its norm. That's the magnitude of r prime. So that's going to be the square root of 3t squared squared, right, plus 4t cubed squared. Okay, so I didn't need quite that much space, but in general, right? So let's just multiply all that out, see what we get. We get the square root of 9t to the 4th plus 16t to the 6th. So there's nothing I can do with the 9 and 16, but the t to the 4th is a common factor, right? So I can factor out the square root of t to the 4th, leaving you with just the square root of 9 plus 16t squared. And the square root of t to the 4th is just t squared. So let me pull that down a little, right? So there we go. So that's the magnitude, that's the denominator. So now we can write capital T, the unit tangent vector. Again, by definition, it's just the derivative of r divided by its norm. Right. So I think at this point, you know, we really do want to split this up, right? So this is going to be 3t squared divided by t squared times the square root of 9 plus 16t squared. That's the first component. The second component will be 4t to the 3, 4t cubed, right, divided by t squared times the square root of 9 plus 16t squared. Right. Right. And at this point, I wish I used the I and j notation, but this is fine too. So the t squares cancel, so this is just 3 divided by the square root of 9 plus 16t squared, and then the second component will be 4 times t divided by the square root of 9 plus 16t squared. Right. So if you'd rather write it this way, you can write it as, say, 3i over the square root of 9 plus 16t squared plus 4 times t times j, it's supposed to be a j, over the square root of 9 plus 16t squared, right? And you can make a case for, you know, writing it all as one fraction, right? So 3i plus 4tj all over the square root of 9 plus 16t squared, right? So as long as you recognize that this is, you know, a vector with two components, then that's fine. In this, in this format up here, oh, sorry, the simplified version here, this is okay too, right, to write it this way. And it's maybe a little bit sloppy to write it this way, right, because those are not the components. Here you're basically saying that each component is divided by the same square root. So, right, so as a warning, I'm really not happy with that notation there. You really should write it this way, even though the denominator is the same. Right? If you do want to write it this way, then I would prefer you use the I and j notation. So, you know, not a big deal, but one of these is fine. Oh, and of course, writing it this way is fine too. Right? You can write the components separately as well. So that's it, right? That's finding the unit tangent vector. Just in most cases, applying the definition, not that bad. All right, so now let's do another one. Okay, so we're given another vector valued function, and we can think of this as the position function. R of t is t times I plus 2e to the t times j plus e to the 2t times k. And this is again for any real number t. Again, find the unit tangent vector, capital T. Right. So, we're going to do it the same way. Just use the definition. So capital T as a function of little t, as a function of the parameter, is just the derivative of r divided by its norm, the magnitude, right? So I think we can pretty much find the derivative pretty easily, right? The derivative of t is 1, so this is 1 times I. And then the derivative of e to the t is e to the t, so 2e to the t times j, right? And then there's a chain rule here, right? So the derivative of e to the 2t is 2e to the 2t times k, divided by the magnitude. So let's take the square root of 1 squared plus 2e to the t squared plus 2e to the 2t squared. And I think we can simplify that. Not the numerator so much, but the denominator. So I'll leave the numerator alone. And notice in the denominator, we're going to have, let's see, square root of 1 plus 4e to the 2t plus 4e to the 4t. Okay, and at this point it looks like that's as good as it gets. It doesn't look like we can factor out anything from all three terms. But if you look at the denominator, or if you look at what's under the square root carefully here, you might notice a little bit of a pattern. As I copy down the numerator one more time. Yep, it's a perfect square. It's the quantity 1 plus 2e to the 2t squared. Right? Yeah, and that obviously doesn't happen very often, right? It didn't happen in the previous case, the 9 plus 16t squared, right? It's the sum of squares, but it's not a perfect square. You cannot split those up, right? Luckily here we can, and in this case we just get, again, same numerator. Now the denominator is really just 1 plus 2e to the 2t. Right. So that's more or less good enough. Or if you'd rather write it in component form, and this could be a while here, right? So the numerator here will just be 1 over 1 plus 2e to the 2t for the first component. The second component will be 2e to the t divided by 1 plus 2e to the 2t. And then the third component will be 2e to the 2t over the same denominator, 1 plus 2e to the 2t. Okay, so either way, right, so that's the unit tangent vector for this particular function. So the point is you can do this for a vector in a plane or a vector with 3 components, right, or 4 components or 5, but 2 or 3 components is pretty much all you're going to see in this course. Okay, so that's it for the unit tangent vector. Now we need to talk about the unit normal vector. Okay, so here's the definition. You have a smooth curve, C, with a parameterization, R of t, right, on some open interval I. If the derivative of the unit tangent vector is not the 0 vector, then you can define what's called the principal unit normal vector, right, n, capital N, as a function of t. It's just going to be the derivative of the unit tangent vector t divided by the norm, right, to make it a unit vector. Okay, so what do we have here? We have our unit tangent vector, pointing along the curve at various points on the curve, right? So the directions will be different, although they could be the same in some cases, right? Okay. All right, so here's a few representative unit tangent vectors, right? All the same length, 1. So now we're going to have the principal unit normal vector. So notice that the first one on the left here, right? If you go a little bit further, notice that the unit tangent vector will be changing in this direction. But as you kind of squeeze it down, right, the derivative will just be how the vector is changing direction. And it's changing direction this way. Right? For the second one, it's changing direction this way. For the third one, oh, this is very close, but I'm going to say just barely this way. Here it's this way. So I think you get the idea. These are going to be our n's, our normal vectors. So you see why we call it a normal vector. It's normal or perpendicular to the tangent vector, right? So these should all be 90 degrees, right? These are going to be orthogonal vectors. Okay? So n and t will be orthogonal. So is that clear? Does that make sense? So let's see if we can reason through this here, right? So remember the whole idea of the unit tangent vector t is that it points along the curve, right? It's essentially in the direction of the velocity. However, its magnitude is 1. And also, if you square that number, right? If you square 1 times 1, you still get 1. So the magnitude squared is 1. And you might remember another way to write the square of the magnitude. It's just the vector dot product itself. Right? So if you take t dot t, you get 1, right? Which is a constant. Does not depend on little t. So let's just take the derivative of both sides. And we know it's a function of t, right? So t dot t is equal to the derivative of 1. Well, the derivative of 1 is 0. And remember, when you take the derivative of the dot product, right, it's the product rule. So you have the first dot product derivative of the second plus the derivative of the first dot product the second. And that's still 0. But remember, the dot product is commutative, so it doesn't matter the order. So this is really just 2 times the dot product of t and t prime. So divide by 2, right? And you get that the dot product of t and t prime, is equal to 0. And that's the definition of two vectors that are orthogonal, right? So t and t prime, the derivative of t, are orthogonal. So that means the vectors will be perpendicular. Okay. Right. Oh, and if you're worried about, wait a minute, but n is not t prime, right? N is t prime divided by the magnitude. But remember, dividing by the magnitude just changes its length. It doesn't affect the direction. Right. So in other words, yeah, it's right. If you take the dot product of t prime and divide by the magnitude, right, the t and t prime. Right. Dividing by the magnitude doesn't affect the angle, right? It doesn't affect the fact that they're orthogonal. So yeah, if t and t prime are orthogonal, then so are t and n. Okay, so I hope that helps. Right. So yes, so this gives us a vector that essentially points in the direction of the change, right? How the curve is changing. And yeah, you know, in which direction it's curving. right? So if you have a curve that's curving, let's say this way to the right, right, then this might be your tangent vector. The normal vector will point this way, right? If the tangent vector points this way, then the normal vector points this way. So why do we call it the principal unit normal vector? Sorry, I should use red here. Right? Because there's another normal vector, right? There's one that points in the opposite direction, this way, or this way, right? Or in the first curve, you can have one that points this way. So it's the same vector, but in the opposite direction. So this will be not the principal unit normal vector, it'll be the negative principal unit normal vector. Or, sorry, negative unit normal vector. Just to abbreviate. Right? So how do you know which is which? Well, it's right, whichever way the curve is curving. If it's curving to the right, the normal vector will point to the right. Right? It's going to point where it's concave. Right? So the one, right, in other words, inward. Right? It's pointing inward, right, not outward. The negative vectors will be pointing outward, or where it's convex instead of concave. So inward is the principal unit normal vector. Outward is the one we don't want, right? That'll be the negative unit normal vector. Okay. Oh, so what if it's not curving? What if you just have a straight line? Right? What if that's your r of t, right? Well, you can define t, right? You can define the unit tangent vector. That's just going to be a vector of magnitude 1 pointing along the curve, right? But notice that if it's pointing along the curve, obviously its magnitude isn't changing. Its magnitude is always 1, and its direction is not changing, which means if you take the derivative, right? If you take t prime, you do get 0. You get the 0 vector. So that's why this condition here is very important. Right? If the derivative of t is 0, right, at any point, in fact, at all points on the line, then you cannot define a principal unit normal vector. Right? You could say it's 0, right, that there just is no unit normal vector. Right? Right. Because it's not curving. Right? So, what would be your principal unit normal vector? This way or this way? If you can't decide, then that probably means there isn't any. Right? And the same is true on this curve here. And I almost wish I didn't do this here. At this point right here, oops, I don't think there's going to be a normal vector. Right? There will be a tangent vector, but not a normal vector at this point. So I'm trying to make this clear, right? Right around here, right, there will not be a normal vector. So let me redraw the tangent vector, points this way, but there is no normal vector. And that's because at this location, the derivative of t will be 0, right? So it's not curving inward, it's not curving outward, right? So it's an inflection point, right? Remember, we used to call these inflection points when the concavity changed, right? If you're going from concave up to concave down, then at the inflection point where it changes concavity, there is no normal vector, no unit normal vector, principal or otherwise. Okay? Because you can see what's happening, right? The normal vectors are going to be pointing inward this way, and then all of a sudden, they're going to point the other way, this way. Right? So at this point, the normal vector makes a big switch, right? It goes from one side to the other side very abruptly. And so, yeah, so at that inflection point, we don't define a normal vector, right? But you still have a tangent vector. So I hope that helps. Okay, so our next example, we have the position vector t cubed t to the fourth as before, and now we want to find n of t. Okay, so there's two ways of doing it. When you have a curve in a plane, right, finding n is really not that hard, right? When you have a curve in space, finding n, finding the principal unit normal vector, is not quite as pleasant. And here's why, right? So we're going to do it the long way first here, right? Now we already found t earlier, right? So I'll remind you of that. Yeah, I think it was in component form, right? 3 over the square root of 9 plus 16t squared. And then the second component was 4 times t over the square root of 9 plus 16t squared. Okay. So how do we find n? Well, now we have to take the derivative of that. So, and then its magnitude as well. So you can see this is not very pleasant. But let's do it. Right? Let's do it anyways. So let's take the derivative, and that just means you take the derivative of each component separately. And so you can use the quotient rule or the chain rule. If you think of this as 9 plus 16t squared to the negative 1/2, right, then you just get, for the derivative, you get negative 1/2, right, times 3 times 9 plus 16t squared to the negative 3/2. Right? And then by the chain rule, the derivative of 16t squared is 32t, right? And that's the first component, unless I'm missing something. I think that's right. And then for the second component, well, that's even worse because now you have a product rule. So let's see. So first times the derivative of the second. So you're still going to get the negative 1/2 times 4t times 9 plus 16t squared to the negative 3/2 times the 32t plus, and then the derivative of 4t is just 4. So 4 times 9 plus 16t squared to the negative 1/2. Yeah, that's nightmares from Calc 1 again, right? So yeah, let's see if we can clean this up a little bit here, right? So 32 divided by 2 is 16. 16 times 3, I think, is 48. So you're still going to get, 48t in the numerator, and then in the denominator, it's 9 plus 16t squared to the 3/2. And then for the second component, well, let's see. We're going to get 16 times 4, so 64t squared, and then plus 4 all over 9 plus 16t squared to the 3/2. But no, I'm missing something here, right? This is going to be to the 3/2 times itself, right? So times 9 plus 16t squared, right? So that divided by 9 plus 16t squared to the 3/2 will be to the negative 1/2. So yeah, not entirely pleasant here, right? Oh, and I'm forgetting a negative sign. This was negative 1/2, so there's a negative here, which is good because you'll see that that will cancel with the positive 64t squared. All right, so 48t divided by 9 plus 16t squared to the 3/2. And the second component will just be 36, right? 4 times 9, 36, over 9 plus 16t squared to the 3/2 power, right? Oh, yeah, sorry. No, we're not done yet. We're not done yet. That's just t prime, right? That's just the derivative of t. Remember, to find the principal unit normal vector, you need to take its magnitude. So what's the magnitude of t prime? Yep, not too pleasant, right? So it's going to be the square root of this squared plus this squared. So I don't know what 48 squared is, or t squared, but when you square the denominator, you're just going to get 9 plus 16t squared to the third power, right? And then the same thing for the second component. So we can just add the numerators. The numerator here is just 36 squared to the power 1/2, right? Because you're taking the square root of everything. Right, so 36 and 48 are multiples of 12, so we can take 12 squared out, and then we'll just take the 12 outside the square root. And then what does that leave us with, right? So 4 squared is 16, and then 3 squared is 9. To the 1/2, right? Oh, sorry, this is to the third power. Well, notice that the numerator is just 9 plus 16t squared. It's just in the wrong order, but it is there. And in the denominator, we have 3 of these factors. So obviously, 2 of them will, or 1 of them will cancel. And that brings us to 12, let's see, over, yeah, 12 over the whole thing, right? 12 divided by 9 plus 16t squared to the 1. Right, so 3 minus 1 is 2, but then the square root of that will just be to the power 1. So maybe I shouldn't have even written the parentheses here, right? Okay, well, there we go. That's going to be the magnitude of t prime. Now we can find the normal vector n. We just take what's in brackets up here, right, and then divide by 12 over 9 plus 16t squared. Okay, so 48t divided by 12 is just 4 times t, and then, so what happens is you'll get in the numerator 9 plus 16t squared, so in the denominator you'll still be left with a square root of 9 plus 16t squared. 36 divided by 12 is 3, so you get 3 divided by the square root of 9 plus 16t squared. Phew. So, yeah, what I was trying to tell you earlier is that, yes, calculating n from the definition, right, which is what we did here, is not very pleasant. It can be quite a chore. Even in what looked to be a very simple case, right? Finding t was not that bad. Finding n was like, 3 times worse. It's 3 times as much work, or at least. Okay, so now I can show you the shortcut, of course. So here's the shortcut. So let me just write down t over here. T was what? It was, I think I made a mistake here. Hang on, something's not quite right. Yep, something's wrong. I missed a sign. There's a minus sign somewhere that I'm not sure. Oh yeah, the very first component here, right? This was negative 1/2. So that should be a negative. Right? Negative 48. Negative 48. So yeah, this is negative. Oh, but you're squaring it, right? So that becomes a positive at that point. Right. So the first component of t prime was negative. So that means there's a negative in front of the 4t. Okay. Well, I'm glad I caught that, because that would have been bad. Anyways, right, t itself was 3 divided by the square root of 9 plus 16t squared, and then 4t. So when you compare t and n, you'll notice that they look very similar. In fact, they just kind of switched, didn't they? Well, they didn't just switch. One of them got a negative sign when you got to n, right? So this was a positive 4t for the tangent vector. In fact, they were both positive components. So notice what happens. We essentially just switch them, switch the components. The x becomes the y becomes the x, right? And then we get a negative sign. So the tricky thing is figuring out which one gets the negative, right? Is it the 3 or is it the 4t? So for that, you have to go back to the original function. The r of t was t cubed t to the 4th. Okay, so let's go back to that for a second. Oops, right, as a vector. So we can draw the curve here. It's just in a two-dimensional plane, the xy plane here, right? And so x is t cubed and y is t to the 4th. So what's y in terms of x, right? Well, t is just the cube root of x, right? It's x to the 1/3. So y is going to be, well, x to the 1/3 to the 4th power, or x to the 4/3. So, right, that's the curve we just want to graph, y equals x to the 4/3. And it's going to look, well, something like this, right? So, right, so that's c. This is just y equals x to the power 4/3. And so, well, let's see. If x is negative, I think it's doing the same thing, right? Is this defined for negative x? It's kind of sloppy, but I think it is. Yeah, again, t can be positive or negative. So that means the x can be positive or negative. Okay, so I think that's the curve. All right, so pick any point on the curve, right? Pick any point, say right here. We have our unit tangent vector t. So which way is n pointing? Remember, n has to point inward. So that's this way. Okay, not this way. That would be outward. That would be negative n. Okay, so notice that for t, both components are positive, right? Because t is positive here. So that means the x component is positive, the y component is positive. So when you're looking for the vector n, you switch the components, you switch the x's and y's, and now you can see where you get a negative sign, right? Because this is pointing in the direction of negative x, but positive y. So that's what tells us that it's the first component that gets the negative and not the second. Okay. So that would have been much easier than going through all this algebra, all this calculus, right? Yep. So to summarize, right, if you have a parametric function, a vector valued function with only two components, let's say x and y, right? Then you can easily calculate capital T, the unit tangent vector, right? And I won't write it down, but it's, oh, okay, I'll write it down, right? It's going to be square root of x prime squared divided by the square root of x prime squared plus y prime squared. I don't think there's a square in the numerator. Let me just make that clear that there, yep, it's just x prime, not x prime squared. Yeah. All right, so it's going to be a bit of a mess here. So x prime, right, of t. And then y, the second component will just be y prime of t divided by the square root of x prime squared plus y prime squared. All right. In any event, right, that's, yeah, so that's not hard to calculate. What's very hard to calculate, as we saw, is n of t. Right. So, right, so let's simplify this. Let's say this is just, t1 and t2. Right. So n is either going to be negative t2, t1, or it's going to be positive t2 and then negative t1. Okay. So yes, once you calculate the components of t, the tangent vector, right, getting the normal vector is just a matter of switching the two components and then figuring out which one is negative. And to figure out which one is negative, you need the graph, right? You need to see which way the curve is curving, right? And based on that, we can see that, right, that T1 here, oops, sorry, so T1 is positive, T2 is positive, right? But for n, right, the T2 now will be negative, and the T1 will be positive. So I hope that helps. Yep. Now, unfortunately, this only works because you have a curve in a plane. If you have a curve in space, right, if you have a vector-valued function, say, with 3 components, then this little shortcut doesn't work at all, because now you have 3 components, right? It's not a matter of just switching them. I mean, that may end up happening. You may permute the 3 of them, but it's not going to be that clear. So, right, so for a curve in a plane, we can see which direction it's curving in. Imagine, draw a curve in space, right, like a helix, and you'll see that if this is the unit tangent vector, that the normal vector, it's very difficult to see which way it's curving inward. So it's very difficult to get based on the graph. So no, if you have a vector-valued function in space, then the only way to do it, unfortunately, is by the definition up here. And we know what a nuisance that is, don't we? Unfortunately, that's the only way to do it that I'm aware of. Okay? Okay, so here is a curve in space, right? It has 3 components, find n. So we're going to have to go through this one more time. And there's no shortcut to this, right? So the good news is we already found t earlier. So maybe I'll just remind you of what t is. So yeah, we'll write it in component form, I guess. Oops, sorry. So 1 over 1 plus 2 e to the 2t, and that's the common denominator, right? Then we had 2 e to the t over 1 plus 2 e to the 2t, and then we had 2 e to the 2t all over 1 plus 2 e to the 2t. Right, so that's the tangent vector. Now to find the normal vector, well, before we do that, we need so remember, n was just the derivative of the tangent vector divided by its magnitude. Right, and it's already bad enough to take the derivative of t, but then to take the magnitude is, well, it's a bit excruciating, right? So let's go through this. Each one of these, of course, is a quotient rule. So you just get the denominator squared. And so, yeah, so this is really just negative 1 over 1 plus 2 e to the 2t squared. No, I'm forgetting the chain rule, right? I'm forgetting the chain rule. So it's going to be negative 4 e to the 2t. All right, and then this will be not just a chain rule, but a product rule as well. So you get denominator times the derivative of the numerator. I'm going to try to write small here. Denominator, derivative of numerator. Yep, minus numerator times the derivative of the denominator. And the derivative of the denominator is 4 e to the 2t. Yep. And finally, the last one here. Denominator, derivative of numerator, minus numerator is the derivative of the denominator. Yep. Right, the rest is just simplifying. And I think for the first one, we're more or less done here. Oh, I'm really not going to like writing this over and over again, but don't have a choice. So here, let's see if we can figure this out quickly. This is going to be 2e to the t plus 4e to the 3t minus 8e to the 3t. So I think we get 2e to the t and then minus 4e to the 3t. So we can factor out a 2e to the t, right? So let me try that again. 2e to the t. So we just get 1 minus 2e to the 2t. Same denominator. Oops, over and over. All right. And then for this one, let's see, we get 4e to the 2t plus 8e to the 4t minus 8e to the 4t. So that's nice because that adds up to 0. And now we just have 4e to the 2t here. Okay, so that's t prime. Now we need its magnitude. Oh, again, not pleasant. So it's one big square root. So you got to square all these things here. Oh, and you know what? We can just square the denominator because that's our common denominator to the 4th power, right? Right, plus, and then you square this, you get 4e to the 2t, and then, well, you multiply all that out, and you get that, and then plus 16e to the 4t. All to the power 1/2, that's the square root. So, what do we get in the numerator? We get 16e to the 4t plus 4e to the 2t minus 16e to the 4t plus 16e to the 6t and then plus 16e to the 4t. To t, sorry, that looks like a 4 here. There's the 4, all right. Well, this is looking a little bit better because 16 minus 16 is 0, and yeah, they're all different terms here. I guess we could factor out a 4e to the 2t, right? And we get 1 plus 4e to the, well, let's do the second one first, right? So 4e to the 2t, and then plus 4e to the 4t. Oops, to the 4th. And you notice what's in parentheses in the numerator is indeed a perfect square. It's 1 plus 2e to the 2t, the whole thing squared. And of course, that cancels with the denominator. And, well, let's just take the square root already, right? So 2e to the t over 1 plus 2e to the 2t, yeah, just 1, right? So I don't need parentheses. Okay, so there you go. That's the magnitude. Ooh. All right, so let me just copy that down up here. Or better yet, let me copy down the t prime, if I can. Oh, yeah. Okay, there you go. There's t prime, and now we just multiply by the reciprocal of its magnitude, right? So this is t prime, and then take the norm. So for our n, what do we get? So negative 4 e to the 2t divided by 2 e to the t is, I think, negative 2 e to the t, right? Divided by, well, I don't need parentheses anymore, right? So it's just 1 plus e to the 2t. 2 e to the 2t, sorry. All right, and then the 2 e to the 2t's cancel. You still get 1 minus 2 e to the 2t divided by 1 plus 2 e to the 2t. And then 4 e to the 2t divided by 2 e to the t is 2 e to the t divided by the same denominator. So there's our answer. So that's the principal unit normal vector for this example up here. The same one we did in example 2, where we found the tangent vector. Now we found the normal vector, and as you can see, this was way worse. Right, but you can see, so let me copy down t again. Right, so unlike in the previous example, there's no good relationship between the t and n here that I can see, right? So there's no, in other words, there's no shortcut. That would have been nice if there was, but the only way that I'm aware to do it is directly this way. Oh, there are formulas, of course. So that there are other ways of doing this, and you can probably find them in the book, in the exercises probably, and that probably would have been a little bit easier than going through all this. So yep, there are formulas for n that don't involve the original definition. I keep going back and forth, sorry about that, but this is the original definition of n, and so we calculated n directly using the definition. Okay, so look, fortunately, I don't think you're going to have to do this all that much. There might be one problem in the homework where you have to do this, maybe. So I would work it out once and then hopefully never again, right? So yeah. So and if you want to use the formula to calculate n, it's still a lot of work, but probably not as much as this, not as much as we did in this case here. Okay, one good way to check, of course, and this, I don't want to, spend forever on this, but let's just make sure that t and n are indeed orthogonal, right, by taking their dot products. So at this point, taking the dot product should be pretty easy, right? Everything's going to be the denominator times itself, right? The denominator squared. In the numerator, you just get negative 2 e to the t plus 1 minus 2 e to the 2t plus, oh, sorry. So, yeah, so 2 e to the t times the right, so 2 times negative 2, negative 4 e to the 3t, right? And then plus 4 e to the 3t. So looks to me like these add up to 0, these add up to 0. That was a minus sign here, right? Not a plus. So yep, you do get 0. Not as a vector, right? As a number. So yeah. So at least that's a good indication we got it right, because the tangent vector and normal vector have to be orthogonal or perpendicular, right? Or normal to each other. All right, let's just move on. There is something called a binormal vector, usually B, and it's just the cross product of t and n. And you know that the cross product will be orthogonal, right? So B will be orthogonal to both t and n. Right. And again, this only applies to a curve. Well, no, it applies to a curve in a plane as well, in which case B is just going to point, well, upward. So if this is your curve, C, right, you have your T here, your N will point inward like this, and T cross N will be pointing upward by the right-hand rule, right? I'm sorry, B, not N. B will be pointing upward, right? And I don't know. I think you have to, I think I'm missing something in the definition here. I think you have to divide by its magnitude because it's not guaranteed to be 1. It's not guaranteed to be 1. So we want to make it a unit vector. Right. Or if you don't mind it not being a unit vector, then you don't have to divide by its magnitude. So, all right. So let me fix that officially here. Right, so there's the usual binormal vector as a unit vector. And if you have a curve in space, of course, say like a helix or something, then T, N, and B form what's called a moving frame. You have your tangent vector, your normal vector points inward, and then your binormal points perpendicular to that, although it's on a little bit of a tilt here, so I think it should be pointing something like that. Right. And of course, all three vectors, as you move around the curve, as you move up the curve or up the helix, all these vectors will change, right? At this point up here, let's say here T points this way, N points this way, and then B will point, not quite, perpendicular to both, to the plane in which B and to which N and T exist, right? So B will always be orthogonal to both N and T. In fact, right, they're all mutually orthogonal. They're all mutually perpendicular. Right. So in other words, T dot N we know is 0, B dot N will be 0, and T dot B will be 0. Right. So they're all orthogonal. Yeah, we're not going to spend a lot of time on the binormal vector. In fact, it might come up in some of the homework or some of the challenge questions, but mostly T and N, right, are the vectors we care about, the tangent and normal vector. We're not going to deal with the binormal vector in this class. Okay, now we get to the all-important theorem, this property. This is something I think I alluded to in the previous video, but I don't remember for sure. Okay, so we have some smooth curve, and it could be a curve in a plane or a curve in space. Right, so this is our C here, right? And we're guaranteed that the normal vector exists, right? Right, at least at all points where you don't have an inflection point. So let's suppose that doesn't happen, right? So for all the points where you don't have an inflection point, right? So this has to do with the acceleration vector, right? Acceleration is just the second derivative of the position vector, right? So this vector, the acceleration vector, has to lie in the plane spanned by T and N. Okay, so at any given point, you have your T, right? You have your N, and those two vectors span a plane. Okay, at each point, you might get a different plane, of course, but at a given point, right, at a given point P here, let's say, right, you have T and N, and of course, right, we talked about B, but we're not going to do that here. B would just be perpendicular to that plane. Okay. But what's important here is that if we were to draw the acceleration vector, and again, we have no idea what direction it's in, but it's got to be in the same plane, right? It can't come pointing out of the plane like this. Right. Okay, so the acceleration vector is in the same plane as t and n. At least that's what the property asserts. That's what it claims, right? I'm going to show that. I'm going to prove it. So in order to prove this, what does it mean for, okay, so let me just show you here. Let's suppose this is the plane. So I'm just going to reorient it so that it's face on, right? So at a given point, we have our n, we have our t. Remember, they should be the same length. I know they don't look like that in this picture up here. They're both unit vectors, right? So what we want to show is that the acceleration vector a, let's try that again. Yeah. Now this vector is in the same plane. And what that means is that we can find a, right, as a linear combination of t and n, right? So we can take the dot product with t, and you get something called little at here. And you can take the dot product of n, and you get something called little an. These are just the usual components. So you can write a as at times the vector t plus an times the vector n. Okay, it's just like a1 times I plus a2 times j. So here t and n are the basis vectors, right? They're like I and j. Even though they do change, you know, going along the curve, t and n will change. They will change direction, not magnitudes, but directions, right? But at a given point, you have your t and n, they span the plane, and a is in the same plane, right? So a will not come pointing, let's say, directly out of the screen or directly into the screen, right? Or even partially out of the screen, right? It doesn't have any z component, right? It doesn't have any component, right, normal to the plane, right? So that's what we want to show, right? And so here's how we're going to do it, right? So let's just start with the definitions of t and n. So we have t, right, which we know is a function of our parameter t. I'm not going to write the little t anymore because it's really just getting in the way. Well, we know these are all functions of little t. Okay, so the definition of the tangent vector is that it's r prime divided by the magnitude of r prime. Right. Or, if you like, because it's the velocity vector, v divided by the magnitude of v. Right. Right. And so we could solve for the velocity vector. The velocity vector is just the speed, the magnitude of v. Oops, sorry, not v prime, but just v. Right. So that's the speed of the object, and times the tangent vector. So that's in the direction of the tangent of the curve, right, of the tangent vector. Yeah. Right. So keep this in mind, right? And so the acceleration then, right, is just going to be the derivative of the velocity, right? So yeah, we can write it as v prime, but we're going to do this. We're going to take the derivative of the velocity. That means we have to take the derivative of the speed times t. And that's a product, right? So we need the product rule. So we take first times the derivative of the second, derivative of t, plus the second, which is t, times the derivative, and this is going to be kind of awkward notation here, the derivative of the magnitude of v, the derivative of the speed, all times the unit tangent vector t. Okay. So what's t prime? Well, yeah, so we can write this as the magnitude of v, right, times t prime, right, plus, and then t times the derivative of, boy, I wish there was a better way to write this, but it's just going to be the derivative of the speed, right, times t. Okay, And now what I'm going to do is multiply top and bottom by the same thing. So I'm going to multiply by 1. And in this case, 1 is going to be of the following form. It's going to be the magnitude of t prime divided by the magnitude of t prime. Right, but that's only in the first term. I think the second term we can leave that alone. Okay, so because I'm getting sick of writing this, let's say the magnitude of v is just v, right? So yeah, that way I don't have to write these bars anymore. So this is times capital T, tangent vector. Right. So notice why I did that. In the first term, this should look familiar. This is the definition of n, right? That's our normal vector. So now we have the magnitude of v, which is just v, right, times n, times the magnitude of t prime, right, plus the derivative of v times t, nope, no prime, right? So there you go, right? We have, and if I could just change the order here, I'll write the derivative of v, the derivative of the speed times t, plus, and then v times the magnitude of t prime. I don't want to write it as t prime, right? So I'll go back to the magnitude of v as well here, just to be consistent. And this is all times n. Okay. So remember, this was the acceleration vector. This was just a. So I think we've accomplished our goal, right? This is a linear combination of t and n. Right? So we wrote the acceleration vector as a t times the tangent vector t plus a n times the normal vector n, where, right, so at is just the derivative of v of course being the speed, and an being this weird thing. It's the speed times the magnitude of t prime. Right, and these things have names, right? This is called the tangential acceleration. Right. So that's at. Right? It's a scalar, right? It's not a vector. It's a component of a vector, right? And an is called the, what else? Normal acceleration. Okay. Yeah. So, right. So what that means is tangential acceleration is what you usually think of when you think of acceleration. So you have some objects, let's say some particle here, and it's moving to the right, right? It's going pretty slow at first, and then it speeds up and goes faster and faster and faster, right? So in other words, the velocity is changing because the speed is changing. The speed is increasing, and if the speed is increasing, it's accelerating, right? So this is what we normally think of as acceleration, something moving faster and faster and faster, right? Of course, you can also, hit the brakes and it can slow down. That's also an acceleration. Some people call that deceleration, but it's just a negative acceleration, right? All right, so that's tangential acceleration, right? It's just the change in the speed. Okay, so what's normal acceleration? Well, normal acceleration will be perpendicular to that, right? So in this case, there is no normal acceleration. If something is speeding up, it's not changing its direction, right? So you get a normal acceleration when you're changing direction, right? So even if your speed is not changing, let's say the speed is constant, right? Oh, that's a little sloppy, right? The speed is not changing, but the velocity is, because the velocity is changing direction. And it's changing direction this way or this way, right? So this will be the normal acceleration. right? Pointing, and remember, they're not vectors, so I have to multiply by n. So these are our normal vectors, right? So these are our principal unit normal vectors. And yeah, so it's possible that the acceleration vector, right, a, could be changing magnitude, right? So it could be shorter here, and then longer here, and so on, right? Maybe not in this picture, but in other cases it could be. Okay, so if you've had physics, right, this is nothing new. You've seen this before, except I don't think you probably haven't called it normal acceleration, right? You would call this centripetal acceleration. That's centripetal with an N. Right, so it's an inward acceleration, centripetal acceleration. So, yep, normal acceleration and centripetal acceleration, you can think of them as the same thing, right? They're essentially the same thing. You only get a centripetal acceleration when you're moving, well, in a circle, right? If you're moving in a circle, let's say with constant speed, right, your acceleration will always point inward. Right? If something is moving in a circle, something has to be pulling it inward, right? If you take a ball attached to a string and you swing it around your head, right? It's going to move in a circle because you're pulling on it, right? You're pulling on the rope attached to the ball. So you're creating a tension. That tension in the rope is the centripetal force, the centripetal acceleration, right? If it's a planet going around the sun, then the centripetal force is provided by gravity. Gravity is pulling the planet inward. Right? Normally, if there was no sun, if there was no gravity, the planet will just be moving in a straight line. Luckily, the sun keeps the planet moving in not a circle, but an ellipse. But an ellipse with a very low eccentricity, so it's almost a circle. It's very close to a circle, but it is an ellipse. Okay, so centripetal acceleration, normal acceleration, essentially the same thing. Okay, so before we move on, these are the definitions of tangential and normal acceleration, but there's probably better ways of writing them. So let's write down all the different ways we can write the tangential acceleration. First of all, the definition is that it's just the derivative of the speed, right? Or you can take the acceleration as a vector and just take the dot product with the unit tangent vector, right? That will also be the component of the acceleration in the direction of the tangential vector. So you can see that up here, right? If the acceleration is this way, right, then a dot t is this vector here. And if you take, right, a dot t is the magnitude of this vector. Right. Remember, a dot t is a dot product. It's not a vector. Right. So the magnitude of that vector is simply that tangential component, at. Right. Or, if you don't want to bother calculating t, you can just take the acceleration vector dot the velocity vector, and then just divide by the speed. Divide by the magnitude of the velocity. So all these are perfectly good ways to calculate the tangential acceleration. Okay, what about the normal acceleration? Well, again, the definition is rather awkward. It's the speed times the magnitude of t prime. Not a very easy way to calculate the normal acceleration. Easier, if you have the acceleration and you have the normal vector, you can calculate it as the dot product in the very similar way that we talked about it up here, right? For the tangent vector anyways, right? But again, remember how difficult it is to calculate n, right? I mean, how tedious that is. So this might not be the best way either. So, right, you can calculate or the acceleration vector, or it could be given to you, and you can probably find the velocity vector. So the way to do it is to take the magnitude of the acceleration, but now you take the cross product with the velocity. Okay? And then take the magnitude of that cross product, and then just divide by the magnitude of the velocity or the speed. Okay, so not quite as easy as the dot product, but it's still probably the easiest way to calculate the the normal acceleration is by using that last formula there. Or actually, there's one more way that I almost forget every time. Right, so the acceleration vector, right, is just the tangential acceleration times t, right, plus the normal acceleration times n. And so if you have I should do this in a different color up here, if you have the magnitude of the acceleration squared, it's just the square of the tangential acceleration plus the square of the normal acceleration. So you can also, by using the Pythagorean theorem here, this is just the Pythagorean theorem, essentially, you can calculate the normal acceleration by taking the square root of the magnitude of the acceleration vector, right, the square of it, and then minus the tangential acceleration. Right. So any one of these will calculate the normal acceleration. Any one of these will calculate the tangential acceleration. Okay, and then maybe we'll do one quick example where we calculate the acceleration and all the tangential and normal acceleration. Okay, so let's go back to the first example we did where we have a curve in a plane, right? The t cubed t to the fourth, right? So we already found the velocity. That's 3t squared, 4t cubed, right? And we found the magnitude of the velocity as well, what I call v, little v, right? Without a vector. And it was what? I think it was t squared times the square root of 9 plus 16t squared. 9t to the fourth plus 16t to the sixth. Yeah, I think that's it. Yeah, okay. And then we can find the acceleration just by taking the derivative again. Now we get 6 times t and then 12t squared. Okay. So we want to calculate the tangential acceleration and the normal acceleration as functions of t, right? So let's start with the tangential acceleration, right? I'm going to use the dot product one, so v dot a divided by the magnitude of v. And maybe I wrote it a dot v, but it doesn't matter, right? The dot product is commutative, so it doesn't matter which way you write it. So this is just going to be, let's see, 3t squared times 6t is 18t to the 3 plus 48t to the 5, all divided by, well, the magnitude of v, which is this thing here. Right? And I think we can cancel 2 of the t's here. So anything else we can factor out? Can we factor out a 2, a 4? No, not a 4. Yeah, I don't know why I'm struggling with this. I think it's a 6, right? So 6t cubed times 3 plus 6 times 8 is 48, right? So 8t squared. Okay. I mean, I do take shortcuts quite often, but this one I felt like I should probably work out more carefully here. So, yep, we cancel 2 of the t's. You just get 6 times t times 3 plus 8t squared, right, all over the square root of 9 plus 16t squared. Right. And now you can plug in any t you want, and you'll get the tangential acceleration at that moment in time. Okay, so that's the tangential acceleration. What about the normal acceleration? So, yeah, again, there's a variety of ways we can do this, right? We're not going to use the normal vector, right? Right, so it's a dot n, but we did find n. That was a while ago, but I forgot it. So maybe we should just do, well, again, the 2 main ways are to do the magnitude of v cross a or a cross v. Because you're taking the magnitude, it doesn't matter what direction it's in, right? Divided by the magnitude of v. So we did the dot product. Now can we do the cross product? So here's the issue, right? These are vectors in the plane. They don't have a cross product, do they? So unfortunately, we're going to have to invent the third component here. So, right, so v is really going to be 3t squared, 4t cubed, 0 for the z component. And a will be 6 times t, 12t squared, and 0 again. Now we can take the cross product. Okay, so yep, the first component is 0, the second component is 0, so there's only a third component, and it's just going to be, let's see, 36 t to the fourth minus 24 t to the fourth. Oh, that's easy. So that's just 0, 0, and then 12 t to the fourth. So, right, and that's a vector, but we only need its magnitude. So I hope you can take the magnitude of that pretty easily. It's just 12t to the fourth. Yeah. Right, when there's only one component, that component is its magnitude. Right, so then you just divide by the magnitude of v, which is up here. So our normal acceleration will just be 12t to the fourth divided by t squared square root of 9 plus 16t squared. If I remember that right, yep. So you get 12t squared all over the square root of 9 plus 16t squared. And so that is our normal acceleration. Okay. Right, and of course the other way, probably a more complicated way, would be to take the acceleration and then take its magnitude and then square it and then subtract the square of the tangential acceleration. Should get you the same thing. Should be the same thing. Yep, and so I think that's all there is. Obviously, if this thing had 3 components, then it's going to be a little more complicated. And, you know, there might be one of those for the homework where you're doing that, finding the tangential and normal acceleration in terms of t, usually. Although if they ask for it at a specific t, you know, you can take shortcuts and just find the, you know, find the values at that point, right? In other words, if they say, you know, t is equal to 1, let's say, right, then you can find v and t and just take the, you know, the dot product of those constant vectors to get the tangential acceleration, right? But again, you know, you have to find v of t and a of t before you can plug in the 1, if that makes sense. All right, so that's it for this section. And in the next section, we are going to be revisiting this. We're going to be seeing these again. And yeah. So I hope that helps.